Hello and welcome. In this video, I'm going to help you determine the Maclaurin series for cosine of x. So for the cosine function, recall the Maclaurin series is simply the Taylor series centered at 0. And you find that by evaluating the function at 0, adding to it its first derivative evaluated at 0. Actually, let me include a little more information just to help you see the pattern. This would be times x to the 0 power, which is 1. Divided by 0 factorial, and by definition 0 factorial equals 1. This is times x to the 1 power divided by 1 factorial. To that, we are going to add the second derivative evaluated at 0 times x to the second power divided by 2 factorial. And we keep going. So I think you can see the pattern. 0, x to the 0 power divided by 0 factorial, x to the 1 power divided by 1 factorial, x squared divided by 2 factorial, and so on. This exponent matches what derivative we're in, so this is the first derivative, second derivative, third derivative, and so on. So with that, let's begin on the Maclaurin series for cosine. So f of x is cosine x. F prime of x, that is the derivative of cosine, is negative sine x. The derivative of negative sine x is negative cosine x. The third derivative of this function, or that is the third derivative of cosine, is the derivative of negative cosine x, and that's sine x. And then you'll notice that this will just continue. So the fourth derivative is equal to just cosine x. And then, so this pattern will continue. We're just going right back up here every time. All right, so cosine x, f of 0, that is cosine of 0, equals 1. F prime of 0, that is sine or negative sine of 0, equals 0. If you don't remember where I'm getting this from, think back to your unit circle. So on our unit circle here, this is the angle of 0 degrees, which is 0 radians here. The terminal point here is 1 comma 0. X equals cosine of 0 equals 1. Y equals sine of 0 equals 0. See the y value here. 0, the x value 1. Okay, so that tells me that the second derivative, which is negative cosine of 0, is equal to negative 1. The third derivative is going to be 0. And then, of course, the pattern is going to repeat again because the fourth derivative is going to go right back up to cosine. So f of x is equal to 1 times x to the 0 power over 0 factorial plus 0 times x to the 1 power over 1 factorial plus our second derivative evaluated at 0 here, that's negative 1. So negative 1 times x squared over 2 factorial plus our third derivative is 0 times x cubed over 3 factorial plus, and let's keep going because for our fourth derivative is going to be cosine of x, so this will also be the fourth derivative here. So this is 1 times x to the fourth over 4 factorial plus 0 times x to the fifth over 5 factorial. And I'll do one more here. This would be minus, so plus a negative x to the 6 over 6 factorial, and then we'll keep going. So f of x, which is cosine of x, is 1 plus, well, these all vanish, all the odd terms. We are left with just the even terms. And this first even term is not a plus, it's a minus. So it's minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6 over 6 factorial. I think we can all guess what the next term would be x to the 8th over 8 factorial. And let's go ahead and write this in summation notation. So we want our negatives to alternate. So we want a -1. When n is equal to 0, we want it to be positive. So I can put an n here for that. When n is equal to 1, we want it to be negative. So this works. Okay, and we can verify that this is correct. Remember, this is n equals 0, n equals 1, n equals 2, n equals 3 term. If n equals 2, -1 squared is certainly a positive. If n equals 3, -1 cubed is certainly a negative. Okay, so our signs work out. Now, for the exponent, we want everything to be even, and even numbers can be expressed by doubling integers. So if n equals 0, we get the 0 power, so no x. When n equals 1, we get 2. When n equals 2, we get 4. This works. And now for our denominator, it's going to be identical. We want 2n factorial. Okay, let's determine the interval of convergence. And for that, we're going to use the ratio test. Okay, so remember the ratio test looks at this limit as n approaches infinity of the ratio of the nth term, or excuse me, the n plus 1 term with the nth term. And as long as that's less than 1, then we know that this series converges. Okay, so our nth term, that's equal to -1 to the n times x to the 2n divided by 2n factorial, and our n plus 1 term is equal to -1 to the n plus 1 times x to the 2. And now we're going to put the n plus 1 in parentheses, since we need to be sure that we distribute this to get 2n plus 2. And then the same thing in the denominator, 2n plus 2. I went ahead and distributed our n plus 1 in parentheses. This would have been the same one here. Okay, let's take a look at the limit. This is the limit as n approaches infinity of the absolute value. And I'm going to go ahead and skip a step. Remember, if I'm dividing fractions, I can write this as a over b times d over c. That is multiplied by the reciprocal. And in order to save some space, since I'm almost out of space, I'm going to go straight to multiplication of the reciprocal. So the reciprocal of the nth term. So this reciprocal. Additionally, you'll notice that I got rid of the negative ones because no matter what, we're going to get a positive or a negative from these, no matter what. And we're in an absolute value, so we don't need them. And let's go ahead and simplify the x's first. This ends up being, that is, x to the 2n plus 2 divided by x to the 2n. Well, this is just x squared. And since this limit is concerned with n's and not x's, I went ahead and pulled that out. And we're going to multiply this by the limit as n approaches infinity. Now I can simplify the factorials. 2n factorial is equal to 2n times 2n minus 1 times 2n minus 2, and so on. Not plus, excuse me. This is multiplication until we get to multiplying by 3, by 2, by 1. We're basically multiplying by the original number less 1 until we get to 1. So let's look at 2n plus 2 factorial. This is 2n plus 2 times 2n plus 2 minus 1, which is 2n plus 1, times 2n plus 2, so 2n plus 2 minus 2, which is just 2n, times 2n plus 2 minus 3, which is just 2n minus 1. And I'll stop there all the way until we multiply by the integer 1. And as you can see here, this part, this is just 2n factorial. Well, what does this tell me? This tells me that 2n plus 2 factorial is equal to 2n plus 2 times 2n plus 1 times 2n factorial. So let's deal with that inside the limit. I have 2n factorial divided by 2n plus 2 times 2n plus 1 times 2n factorial. Okay, well, the 2n factorial divided by 2n factorial, that's clearly 1. And what we end up with is the limit as n approaches infinity of 1 over 2n plus 2 times 2n plus 1. Well, no matter what x is, this limit's going to be 0, which is less than 1. So the value of x does not matter. That is, what converges? Well, this series converges for all x. That is, the interval of convergence is from negative infinity to infinity. Another way to say this, it's equal to all real numbers. Keep calm and math on.